We begin with those controversial videos known as deepfakes.
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 Videos that look so real, it's hard to tell what's fake.
David, I mean, I know you're a sophisticated guy. The world is a mess. The world is as angry as it gets. Well, you think this is going to cause a little more anger? The world is an angry place.
The internet just got a major wake-up call. President Trump has backed the Take It Down Act, a landmark move against revenge porn and deepfake abuse. This bill is a historic win for victims whose images have been weaponized using AI. Predators who spread this exploitative content will now face serious criminal charges, and big tech platforms can no longer turn a blind eye. Let's hear what President Trump said while signing the act.
Today, it's my honor to officially sign the Take It Down Act into law. It's a big thing, very important, so horrible what takes place. This will be the first ever federal law to combat the distribution of explicit, imaginary, posted without subject's consent. They take horrible pictures, and I guess sometimes even make up the pictures, and they post it without consent or anything else. And very importantly, this includes for forgeries generated by artificial intelligence known as deepfakes. We've all heard about deepfakes. I have them all the time, but nobody does anything.
That's an excellent move. AI-driven crimes are skyrocketing. And deepfake technology is advancing at an unprecedented pace. With the rise of transformers and diffusion models, both image and video generation have become incredibly realistic. In this video, we'll break down the math and machine learning techniques behind deepfake technology, how it works, why it's so powerful, and what makes it so dangerous. But before we dive in, an important disclaimer. This video is for educational and awareness purposes only. I do not support or condone the use of deepfake technology for harmful, deceptive, or exploitative purposes. Deepfakes can be misused to violate privacy, spread misinformation, and cause real harm. The goal of this content is to help viewers understand how the technology works, recognize its risks, and promote ethical, responsible use of AI. Early deepfake methods were built on architectures like variational autoencoders and generative adversarial networks. While these models were capable of producing somewhat realistic images, their limitations in quality and consistency hindered real-world applications. But things have changed. With the emergence of diffusion models, image and video generation has reached a new level of realism. These models have dramatically improved the fidelity and believability of synthetic content, making it almost indistinguishable from real footage. As a result, deepfake technology is now being applied in fields ranging from entertainment and filmmaking to live streaming and even privacy protection. Broadly speaking, deepfake generation research falls into 4 key areas: face swapping, replacing one person's identity with another's in an image or video; face reenactment, transferring expressions, movements, and head poses from a source to a target face; talking face generation, animating a still image to speak using text or audio as input; facial attribute editing, modifying traits like age, emotion, or hairstyle while preserving the original identity. Deepfake generation is a controlled content generation task, where a target image video is manipulated based on specific conditional inputs like images, audio, text, or attributes. Formally, this is represented as generation, where G is the generation network, IT is the target image, and C is the condition. And detection, where D is detection model outputting a forgery score. You can think of it as classification task, predicting if content is real or fake. Variational autoencoders introduced probabilistic latent spaces, enabling smooth interpolation and new content generation. Conditional VAEs extended this by allowing generation under specific inputs, while VQ-VAEs improved latent representation learning using vector quantization. These models significantly advanced the quality and control of AI-generated content. Generative adversarial networks use adversarial training with a discriminator to produce high-quality images. They remain a core method in deepfake generation. Variants like conditional GANs allow controlled outputs, Pix2Pix improves image-to-image translation, and StyleGAN and StyleGAN2 bring high realism and fine control through style-based generation. Diffusion models generate data by simulating a gradual denoising process. Models like denoising distribution probability model stand out for their ability to produce high-quality, high-resolution images. Latent diffusion model improves flexibility and handles complex data distributions more effectively. In video generation, diffusion models are becoming essential. Approaches like stable video diffusion fine-tune image-to-video tasks based on powerful text-to-video models. Discriminative neural networks play a crucial role in deepfake detection. Unlike generative models, these are designed to classify, analyze, and detect forgeries in visual data. One powerful architecture in this space is the Swin transformer. It addresses a key limitation of standard transformers: their inefficiency in handling high-resolution images. Swin transformers use a hierarchical structure with shifted windows, allowing them to scale better and capture both local and global features effectively. Neural radiance fields, or NeRF, introduced in 2020, brought a major shift to 3D scene reconstruction. By combining volume rendering with implicit neural representations, NeRF captures both geometry and lighting with impressive realism. Compared to traditional 3D techniques, it delivers significantly higher visual quality and is now used in tasks like 3D geometry enhancement, object segmentation, and 6D pose estimation. So in the paper, they talk about some of the dataset they used, so I guess Caleb dataset, VGG face, and so on. They also have a very detailed table on the dataset. For deepfake generation tasks, commonly used metrics include peak signal-to-noise ratio, structured similarity, lip-sync distance, identity retrieval rate, and so on. Lip-sync distance evaluates how accurately lip movements match the audio and talking face generation. Identity retrieval rate checks if the generated face retains the original person's identity, often using face recognition models. VAE-based methods typically use reconstruction loss and KL divergence loss, with common losses including mean squared error, cross-entropy, LPEPs, and perceptual loss. GANs add adversarial loss to boost realism, while diffusion models rely on denoising loss to guide generation. AI face swapping has evolved fast. Early GANs struggled with pose and lighting. Models like DepthNets and FSGAN improved realism, but had trouble with occlusions and generalization. High-res models like MegaFS and StyleIPSB boosted detail, while HifaFace and FlowFace++ focused on preserving 3D facial structure. Newer diffusion-based models like DiffSwaps and FaceX now deliver ultra-realistic results by treating face swapping as a conditional in-painting task. Face reenactment techniques aim to transfer expressions and head movements from one face to another. They generally fall into 4 categories. Landmark matching methods rely on facial key points to map expressions and gaze. Models like X2Face and FreeHead enable precise control over face and eye motion, even in challenging head poses. Feature decoupling approaches work in the latent space, separating identity from motion or expression. Models like HyperReenact and StyleMask fine-tune facial movements without losing identity. Talking face generation aims to create realistic videos of people speaking based on audio, text, or multiple inputs. Approaches fall into 4 main categories. Audio/text-driven. These models sync lip and facial movements with speech. Early methods lacked generalization, but newer ones like SadTalker and MakeItTalk use 3D motion and facial landmarks for more natural results. NeRF-based models are used to simulate dynamic 3D faces, while diffusion-based models like DAE-Talker and VAS-1 offer high-resolution, emotion-aware video generation without relying on explicit 3D components. Forgery detection approaches aim to identify manipulated or AI-generated content by analyzing visual, temporal, and semantic inconsistencies. Common methods include artifact-based detection, which looks for visual flaws like unnatural textures, frequency domain analysis to spot anomalies in signal patterns, and temporal methods that catch inconsistencies across video frames. More advanced approaches use identity consistency checks, cross-modal analysis to verify lip sync and audio alignment, and transformer-based models for capturing subtle manipulations. Emerging techniques also leverage self-supervised and few-shot learning to adapt to new types of deepfakes with minimal labeled data. This video is already packed with a lot, so let's take a break here. In the next episode, we'll dive into how to actually design a deepfake video from scratch. I'm thinking, what if we make Elon Musk versus Mark Zuckerberg face off? Ed's Messi versus Ronaldo on the football fields? That should be fun. Stay tuned. See you in the next one.